Mm-hmm. Exactly. Exactly. So, friends, we did discuss about the fundamental radiation laws, like Planck's theory and Wien's displacement law. We also discussed about the Kirchhoff's laws of radiation, where effective emissivity is equal to absorptivity, that the properties of material like absorptivity, emissivity, and transmissivity, reflectivity and transmissivity we have discussed. And emissivity, different kinds of emissivities we have discussed. Monochromatic emissive power and intensity relations, intensity of radiation relations, we have discussed in the last class. Also, towards the end of the last class, we were talking about the radiation shape factors. Now, when we are talking about radiation heat exchange between two surfaces, there is no guarantee that all the radiation leaving one will go and fall on two. And similarly, the equal amount of radiation which is intercepted by two may not be falling on one because of the geometries of the surfaces. So, the radiation view factor will form an important parameter in calculating the radiation heat exchange between surfaces. And that's how we have formulated certain rules, the summative rule, f of I of I plus f of I of 1 plus f of I of 2 up to I of n, if it is interacting with n, should be equal to 1. That means the radiation leaving surface 1, if it is exchanging heat with only n surfaces, then the radiation sum of all the radiation shape factors, including radiation shape factor of the same surface, meaning the radiation emitted from surface 1 falling on the same surface. I told you a curved surface. The radiation A2, F2 to 1 should be equal. And of course, there is Stefan Boltzmann's law. Now, between two black surfaces, when we are talking about, let me say, please excuse. Okay, let me say there are two surfaces, 1 and 2. Each one has a shape factor towards the other, and the areas and temperatures are defined. It is okay. So Q1 to 2 means the net radiation heat exchange between 1 and 2. That is the idea. So radiation leaving the entire surface 1, the surface 1, that strikes surface 2. What is radiation leaving the surface? EB1, if both are assumed to be black surfaces, EB1 is the emissive power of a black body at a given temperature. So its temperature is known. What is EB1? Sigma T1 power 4. EB1 is equal to sigma T1 power 4. What is the surface area? A1. And EB1 into A1 amount of radiation is going towards it. How much is going to fall on that? F1 to 2. Radiation shape factor between 1 and 2, F1 to 2. So, a radiation amount of EB1 multiplied by A1 is leaving surface 1. And F1 to 2, if it is a fraction, that fraction is intercepted by 2. Now, what is the second surface? Second surface is also a black body. What is a black body's definition? It absorbs all the radiation that's falling. What is the radiation intercepted by this? EB1, A1, F1 to 2, which is leaving from surface 1, falling on it. And by virtue of its nature, black surface, it absorbs all the radiation that's falling. So, what is the radiation exchange from 1 to 2? It is A1, EB1, F1 to 2. Similarly, Surface 2 is at temperature T2. So therefore EB2 is leaving the surface 2. What is EB2? Radiation emitted per unit area. What is EB2? Sigma T2 power 4. And what is the surface area? A2. So sigma T2 power 4 A2 amount of radiation left surface 2. And how much is reaching surface 1? Shape factor F2 to 1. So F2 to 1 is multiplied. Now, surface, some radiation is leaving surface 1. Of that, some radiation is intercepted and absorbed by surface 2. Similarly, some radiation is leaving surface 2. Only a fraction of the radiation leaving surface 2 is intercepted and absorbed by surface 1. And therefore, they both are gaining heat by virtue of the net radiation heat exchange between them. So what is the net gain or net loss for each surface? Magnitude tells you, depending on which is the higher temperature, which is the lower temperature. So the difference between this will give you the total radiation exchange between the surfaces. Q1 to 2 is A1 F1 to 2 sigma T1 power 4 minus T2 power 4. Why A2 F2 to 1, where it has gone? I applied reciprocity theorem. What is reciprocity theorem? A1 F1 to 2 is equal to A2 F2 to 1. A2 F2 to 1, I substituted with A1 F1 to 1. Okay. So now if a surface 1, surface J is interacting with n surfaces, let me say, then sigma of AI F1 to J, Qi, the total amount of surface radiation leaving the surface I, Qi, is equal to sum of all the radiation shape factors into sigma T1 by Ti power 4 minus Tj power 4. Okay. Diffuse gray surfaces. Most enclosures encountered in practice involve non-black surfaces. The black body, as I've told you, was only an ideal body, and you don't find these ideal bodies too often. Radiation analysis of such enclosures becomes very complicated unless some simplifying assumptions are made. Okay. So now we need to make a certain simplifying assumptions, but when you complicate it, it will be really complicated. Now, if you say it is transparent, if it say it is opaque, it is absorbing, it is diffusing, it is specular, kind of various things. Now, it is common, normally in all these cases, we assume that surfaces are opaque. They are not allowing radiation to pass through, basically, unless otherwise. Right? And they have diffuse reflection, meaning I've talked to you about two kinds of reflections. One is specular reflection, another one is diffuse reflection, and another one is the gray surface. Also, each surface of enclosure is isothermal, meaning every surface will be at a constant temperature. Temperature is not varying during the radiation heat exchange process, and both incoming and outgoing radiations are uniform over each surface. So these are the simplified assumptions that we make here. Now, I would like to derive a generalized equation. Now, I define two terms to you right at this point of time. That is the incident radiation, I call it as irradiation, G, watts per meter, so many watts per meter square. How much of radiation from elsewhere? See, my palm is a surface. It is receiving radiation from this bulb, this roof, this laptop, this wall, this curtain. It's receiving radiation from various sources. So cumulatively, all the radiation falling on surface 1, I call it as incident radiation or irradiation G. Now, irradiation G, when it is falling, the material may have an absorptivity of alpha and reflectivity of rho. Okay. And when G is falling on it, rho G, if reflectivity is rho G is reflected back, remaining thing is absorbed, because I said it is opaque, it is not transmitting anything. So therefore, alpha plus rho should be equal to 1. Tau is made 0. Opaque, when I said, tau is 0. Now, G is falling on it, some alpha is absorbed, alpha G is absorbed, and rho G is reflected. It's common case. What is rho in terms of alpha? Rho is 1 minus alpha because rho plus alpha is equal to 1. Normally, ఏంటి relation మనకి rho plus alpha plus tau is equal to 1. Here tau is 0 because it's a opaque surface. So rho plus alpha is equal to 1. What is rho? Rho is equal to 1 minus alpha. What is Kirchhoff's law? Rho alpha is equal to epsilon, m/50. So rho is replaced by 1 minus epsilon. Okay. And this much amount of radiation is leaving the surface. What is this rho g? Rho g is the reflected component of the, because the surface is receiving radiation from various sources, and of that amount falling on the surface, rho g is reflected, meaning it is not taking that energy. The surface is receiving energy from various sources. Rho g, it is not taking it, it is sending it back. Fine. Now what is happening? It is absorbing a radiation of alpha g, and therefore its internal energy is increased. It has a surface temperature now, and at this surface temperature where it is maintained, it is emitting radiation. How much it is emitting radiation? If it is a black body, it would have emitted EB. What is EB? Sigma T power 4. If it is a real surface, it would have emitted emissivity times EB. Understood? What is emissivity? Emissivity is radiation emitted by a real surface to that of a black body. For a black body, it is 1. For all real surfaces, it's less than 1. So, 1 minute. Emissivity is equal to emissive power of a real surface divided by emissive power of a black body. A real surface and a black body, both are maintained at the same temperature T. Okay. Now, E is coming out of this. It's a real surface. This is a black surface, EB is coming. What is EB? Sigma T power 4. EB is sigma T power 4. So, therefore, emissive power of a real surface is always given epsilon times EB. Emissive power multiplied by emissive power of a black body. Okay. So, there is no confusion over it. It is epsilon times EB. So, what is this total amount of radiation leaving a surface? I call it as radiosity. When I talk about radiosity, I am talking about reflected component of radiation leaving a surface and also emitted component of radiation leaving a surface. Reflected component of radiation leaving a surface and emitted component of the surface. Because there are two different things. See, some radiation is coming, it is not accepting it. It's some part of it, it is sending it back. Nothing to do with it. The incoming radiation is reflected, sent back. That is coming out of the surface. And also by virtue of its surface temperature, it is emitting radiation. So two things are coming out of the surface. One is reflected component, another one is emission component. Whenever I talk about radiosity, I talk about these two components, reflected radiation and emitted radiation. So radiosity J, I use the symbol, irradiation, I use the symbol G. Both are defined so many watts per meter square, meaning per unit area. So irradiation is radiation emitted by a surface and radiation reflected by a surface. What is radiation emitted by a surface? Just now I have explained. It is epsilon EBI. What is radiation reflected by the surface? It is rho GI. Rho GI is 1 minus alpha. From Kirchhoff's law, 1 minus emissivity. So that's how I define. For a black body, if it is a black body, what will happen? Any black body can only emit radiation which is equal to EB. Black body emission is EB. Only EB comes out. Where is the reflector component? Because black body will not reflect any radiation. Rho is equal to 0 for a black body because alpha is equal to 1 for the black body. Alpha plus rho plus tau is equal to 1. When alpha is 1, rho is 0 or tau is 0. So, a black body will not reflect any radiation. When I talk about the radiosity of a black body, it is all about radiation coming out from a black body. So, from this equation also, for a black body emissivity is equal to 1, I substitute emissivity is 1. So, the reflector component becomes 0 and this is 1. GI, radiosity, leaving the surface is only the emissive power of the black body. So, I just talk about, introduce these terms irradiation and radiosity. Don't get confused. Irradiation is the total amount of radiation falling on the surface, which we treated as incoming radiation, and depending on the surface, if it is a black one, everything is absorbed of the incoming radiation. If it is a real one, some part of it is reflected. What is reflected? Rho g is reflected, and in addition to that, emission is taking place from any surface, be it a black body and real surface. So radiosity is sum of the reflected component and emitted component. So these two components form into radiosity. For a black body, of course, it is EB1 or EB of that surface. Okay, now we just make some mathematical jugglery. So what is the net radiation heat transfer to or from a surface? It is total radiation leaving the entire surface minus radiation falling on it. See, J is what? Radiosity. Radiosity is leaving the surface. Irradiation is falling on the surface. So what is the net energy stored or given? It is leaving minus entering, falling. So therefore, A, of course, when it is surface area, because both J and G, irradiation and radiosity are depend per unit area. So the total net radiation heat transfer into or from the system, depending on which is maximum, whether J is higher than G or G is higher than D. If G is higher than J, radiation heat is transferred to the surface. If G is less than J, heat is transferred from the surface. That's how you should take it. So it is AI into Ji minus Gi. And from this equation, you just write an equation for Gi in terms of Ji. Okay. Have you seen this equation? Ji is equal to, which very easily we have calculated. From this, you write an equation for Gi. Okay. So when you write that, everything is in Ji, and ultimately when you sum it up, it is Ei epsilon I divided by 1 minus epsilon I into EBI minus Gi. What is I here? I is a surface. I can be 1, I can be 2, I can be 3. Don't get confused. I stands for the number of the surface. So if you are talking about net radiation transferred from surface 1 across the surface 1, this is the equation. Okay, so from this you can find if it is a negative surface is receiving radiation, net it is receiving the surface radiation. If it is positive surface is giving the radiation. Okay, that's how it is. So Qi is equal to EBI minus Ji divided by Ri. See, ikkada malli manam Ohm's law formula తీసుకుంటాం. Q is equal to. Again, I'm telling you, radiosity irradiation relation ikkada రాసుకున్నాం. Okay, so now net radiation heat transfer from across the surface equation రాసుకుంటే ఎంత వస్తుంది ఎంత వెళ్తుంది, that equation we wrote. For Gi, from this equation we substituted, and therefore we simplified. If finally I got this in form, and Ohm's law form like this kunte, if you think the EBI and Ji are the potential differences, and remaining thing will come onto the denominator, and the surface resistance here, after I call it radiation surface resistance of any surface Ri, is given by 1 minus epsilon I divided by Ai epsilon 1. For surface 1, R1 is equal to 1 minus epsilon 1 divided by A1 epsilon 1, where A1 is the area of the surface 1, emissivity of the surface 1 epsilon 1. That's how it is. So, a surface, had it been a black body, it would be emitting radiation equal to EB, and if it is for a black body, please look at it, emissivity is equal to 1 and resistance is 0. Emissivity is equal to 1 and therefore resistance is equal to 0. So, for a black body, the amount of radiation is EBI. Straight away what comes up is EBI because the resistance is 0. For any other surface, the resistance of the surface, radiation resistance of the surface depends on emissivity of the surface and the area. So, the equations are given. Now, electrical analogy, I have introduced it here. So, now what is radiosity if two, three surfaces are interacting with each other? Two, three surfaces are interacting. Let me once go back. So I said, if it is a black body, there is no JI, only EB1 comes. Let me once again come back to this figure. If it is only a black body, there is nothing like this, and emissivity is equal to 1, only EB comes out for a black body. Only for a real surface, J come out. Okay? Oh, if it is a real surface, only J come out, whereas if it is a black body, EB comes out. J or EB comes out. What is maximum? What is J? I said J is something, what we call it, you see? J is this, right? J is this. So, J is something else. Whereas a black body, if it is a pure black body, this comes out. Whereas if it is J, something else come out. And therefore, there is a resistance coming into picture. Black body is an ideal body. Black body is one which emits maximum possible radiation. So, for any real surface, this resistance comes into picture. For a black body, I have told you there is no resistance. If it is a black body, it is not Ji that is coming out, it is EBI that is coming out. So, when two surfaces are interacting with each other, again, I just use this. When two surfaces are interacting with each other, let me say this is surface 1, this is surface 2. And let me say both are real surfaces. Its emissivity is epsilon 1, emissivity is epsilon 2. The surface area is A1, the surface area is A2. Then, if you want me to write a network, J1 comes out of this. This is radiosity, right? J2 comes out of this. This is radiosity of surface 2. Now, in between, had it been a black body, it would have started EB1. Whereas it's not a black body, it is only coming out J1. And in between, what is the emissivity? Surface resistance 1 minus emissivity divided by A1 emissivity 1. And of the J1, how much is intercepted by J2? Only a fraction of A1 F1 to 2, right? A1 F1 to 2. So therefore, you need to bring in the radiation shape resistance, which I just bring in here. So the radiation shape resistance is between, see, J1 is coming from the surface, J2 is coming from the surface. So entire J1, J2 are not being absorbed by the surfaces. Some resistance is coming in picture. So if I write the equation, let me come back and explain it to you. J1 is moving towards it, J2 is coming towards it. What is Q1 to 2 between them? Is it J1 minus J2? No. Because entire J1 is not falling on 2, entire J2 is not falling on 2. So what is that you write? Q1 is equal, 1 to 2 is equal to A1 F1 to 2 J1, because J1 is per unit area and J1 A1 is the total radiosity leaving the surface, and of that only F1 to 2 fraction is falling on the surface 2 minus A2 F2 to 1 J2. And when I apply reciprocity theorem for A2 F2 to 1, I write A1 F1 to 2. That's equal to A1 F1 to 2 into J1 minus J2. Okay, so Q1 to 2 between the two surfaces when they exchange, when I write it into the Ohm's law form, it is 1 by J1 minus J2 divided by 1 by A1 F1, right? So a shape resistance is coming in picture. What is the earlier resistance that we talked about? Between, it is surface resistance, 1 minus epsilon divided by A1 epsilon 1. And between J1 and J2, between the two surfaces, you always have a shape resistance, which is if two surfaces are exchanging, which is 1 by A1 from the simple equation from here. Okay, from here, I've shown it. From if you apply reciprocity theorem, it can be 1 by A2 F2 to 1 also. Similarly, on J2, there is surface. Second surface also has a resistance, which is EB2. Had it been at a temperature T2, it would be emitting EB2. But since it's a real surface, it is not EB2 that is coming out of it, whereas a resistance of 1 minus epsilon 2 A2 epsilon 2. So, very precisely, this is how you can draw resistances for radiation. And that's what I said. When a surface had it been a black body, EB1 comes, EBI comes out, or EBJ. For simplicity, you can assign I is equal to 1, J is equal to 2. Okay. So EB1, if it is a black body, look at this diagram. Had it been a black body, EB1 would have come out of it. Whereas it's a real surface and therefore surface resistance is coming into picture. What is the surface resistance? R1, I stands for 1. R1 is 1 minus epsilon 1 divided by A1 epsilon 1. And between J1 and J2, I is 1, J is 2. J1 and J2, it is the shape resistance. Shape resistance is 1 by A1 F1 to 2. And between surface 2, had it been a black body, okay, EB2 would have come in, whereas it's a real surface, it is coming. Now, just I wanted to make this also very clear to you. Let me draw this. Okay. So, if I have two black bodies, both are black bodies, okay. So, how much is coming out of a black body? EB1. And that depends on temperature. EB1 is EB is sigma T power 4. మీరు 1, 2 substitute చేస్తారు. And similarly, EB2 comes out of this. EB2 comes out of this. So the net radiation heat exchange between 1 and 2 is only the shape resistance. Because EB1 is coming, EB2 is coming out of the surface, there is no surface resistance because both are black bodies, and therefore there is only one resistance, which is A1 F1 to 2. Or reciprocity theorem apply చేస్తే A2 F2. Okay. A2 F2 to 1. Okay. So this is about a black body. If had it been real surface, two real surfaces exchanging heat, real surfaces which ఎంత వస్తుంది? J1 comes out. And from this J2 comes out, not EB. Do you have still a confusion? Please go here. If you still have a confusion, go here. What comes out of a black surface? If it is black, there is no reflection. MCOT is equal to 1. Only this is 0. MCOT is equal to 1. Only EB comes out. If it is a real surface, rho G comes out and epsilon B comes out. So, what comes out of a real surface is different from what comes out of a black body. For a real surface, only J1 comes and J1, J2 come out, whereas for a black body, only EB1, EB2 comes out. Now, when I talk about, had it been a black body, it would have emitted EB1. What is EB1? Sigma T1 power 4. Okay, that would have emitted. But it's not a black body and therefore it has a surface resistance. So, it is J1. What is the surface resistance? You already know. 1 minus epsilon 1, A1, F1. And between J1 and J2, I get the shape factor, shape resistance. So, geometric resistance, or whatever you call it, view resistance, or whatever. And for surface 2 also there is a surface resistance, 1 minus epsilon 2 divided by A2 epsilon. Agree? Yes or no? So, if it is a black body, when two surfaces are exchanging, only shape resistance comes into picture. For real surfaces, even surface resistance comes into picture. And the third possible case, don't laugh at me, sometimes I'll be too silly. One black body, one real surface, when they exchange heat, what will happen? So there will be two resistances only. Since it's a black body, EB2 comes out, and but this is a real surface. One is a real surface, so there is a surface resistance J1, and this is 1 minus epsilon 1 divided by epsilon 1 J1. So it is J1 EB1 which is interacting between the two surfaces, and the shape factor is J1. Okay, so this is how the shape does. So, I even electrical analogy for space resistance or shape resistance or a view resistance or geometrical resistance, whatever you call it, and they are applied here. So, between two real surfaces exchanging I and J, and accordingly, if any one is black, if one is black, Ri is 0. Black body will not have surface. If you substitute 0, this resistance goes on remaining. So this can be used for a complicated network also. So maybe you can solve any kind of problem in the network. Okay. So the radiation problems, some of the total view factors, when I is exchanging with the J surfaces, so it is, Ji minus Jj, Fi to J, sigma. If it is more than one surface, it is sum of all the shape. Okay. And in a nutshell, so I have already given you these three resistances and Q1 to 2 from surface 1 to 2, starting from EB1 to EB2, because it is easy for me. EB1 is sigma T1 power 4, EB2 is sigma T2 power 4, because both are black body emissive powers. So therefore, sigma T1 power 4 minus T2 power 4 divided by 1 minus epsilon 1 divided by A1 epsilon 1 plus 1 by A1 F1 to 2 plus 1 minus epsilon 2 divided by A2. Okay. So that's how the total resistances come into picture. So this is a generic rule. Maybe friends, I just want you to remember this equation. So when two real surfaces are interacting with each other, forming an enclosure which is forming into radiation heat exchange, the entire radiation network is this, and if this slide you can remember, you can solve many radiation heat transfer problems. You can solve many radiation heat transfer problems. Let me see how it happens. The same equation, what is this? This is the equation. How it changes. If you have a small body object in a huge enclosure, maybe you say this paperweight in the room. This paperweight is interacting with the room. The surface area of this paperweight is very, very small as compared to the enclosure area. So therefore, A1 by A2 becomes 0 when A1 by F1 to 2 is equal to 1. Because, anything that goes from this surface will definitely be intercepted by the enclosure called room. So therefore, F1 to 2 is 0, 1. And when you apply this equation, okay, maybe you take A1 common and take it outside. So it is A1 by A2. A1 by A2 is 0 already, and F1 to 2 is 1, and therefore the equation becomes, sigma epsilon 1, A1 sigma epsilon 1. You wanted to write this expression? Maybe. Maybe did I write it? So you have a surface resistance, you have a shape resistance, you have another surface resistance. starting with EP1, starting with EP2, and 1 minus epsilon 1 divided by epsilon 1 A1, 1 by A1 F1 to 2, and 1 minus epsilon 2 divided by epsilon 2 A2. Okay. Now, between surfaces 1 and 2, let me say I have two surfaces. Now, it all starts from EP1 minus EP2. Okay. Divided by ఇక్కడి నుంచి ఇక్కడికి కదా divided by three resistances 1 minus epsilon 1 divided by epsilon 1 A1 plus 1 by A1 F1 to 2 plus 1 minus epsilon 2 divided by epsilon 2 A2. ఇప్పుడు మన కండిషన్స్ ఏం చెప్పాం a small object in a large enclosure, this is 1, this is 2, and therefore A1 is too small as compared to A2 is 0. A1 by A2 is equal to 0. F1 to 2 is equal to 1. Anything that comes out 1 shall be intercepted by 2. When I substitute that, okay, this becomes EB1 and EB1 minus EB2 and sigma T1 power 4 minus T2 power 4 and divided by 1 minus epsilon 1 divided by epsilon 1 A1. Okay, plus 1 by A1, F1 to 2 ledika, plus 1 minus epsilon 2, oops, 1 minus epsilon 2 divided by epsilon 2 A2, right? So, when I take A1 common, I just need to plan it. Sigma A1 common తీసుకుని పైకి తీసుకెళ్ళిపోతాను. T1 power 4 minus T2 power 4 divided by what is remaining now 1 by epsilon 1 minus 1 ఇక్కడ 1 minus epsilon 1 కదా 1 minus epsilon 1 so divided by epsilon A1 I have taken it out minus 1 ఇక్కడ A1 already తీసేసాను so therefore plus 1 ఇక్కడ ఏమవుతుంది it is A2 is already there plus A1 common తీసుకున్నాను కాబట్టి it becomes A1 by A2 into 1 minus epsilon 2 divided by epsilon 2 అవుతుంది. So what is A2? A1 by A2 0. So therefore this becomes 0. Okay. So minus 1 plus 1 gets cancelled. 1 minus epsilon మిగులుతుంది entire denominator లో. So Q1 to 2 is equal to epsilon 1 sigma A1 into T1 power 4 minus T2 power 4. Okay. So what do I say? If you know that equation, you can apply any kind of a condition into this. That's what I said. You have this equation, you go on applying the conditions. What are the conditions? If a small body is placed in a large enclosure, I take out two conditions. A1 F1 to 2 is equal to F0, F1 to 2 is equal to 1, F2 to 1 is not equal to 1. Okay, so therefore I applied those conditions and therefore the entire equation became so much. If it is two infinitely large parallel plates, very large parallel plates, so that means radiation cannot escape except for something at the edges, ignore them. Two infinitely long, very, very long parallel plates separated by a small distance, then A1 equal to A2 is equal to A, F1 to 2 is equal to F2 to 1 is equal to 1, and when you substitute all these conditions, that's it. You need to remember this equation because you find number of questions asked even in GATE and IES on the heat exchange between two infinitely large parallel real plates. They are real plates. Surface 1 has emissivity 1 and area 1, temperature T1, and infinitely large parallel plates and A1 equal to A2 anukunta. Second surface is at epsilon 2 and T2. Okay, that's how you get it. And infinitely long concentric cylinders. Infinitely long concentric cylinders. So A1 by A2 is in the ratio of R1 by R2. Okay, surface area same avutundi 2 pi RL avutundi. So ratios R1 by R2 avutundi. F1 to 2 is equal to 1. Anything that leaves surface 1 will completely fall on surface 2. The bigger one is 2, smaller one is 1. So, అలాంటి సర్ఫేస్ ఉన్నప్పుడు F12 is equal to 1 and Q12 net radiation heat exchange between them is A1 sigma T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 minus epsilon 2 by epsilon 2. In the condition ఆ general equation లో substitute చేశాను అంతే. So, these are simplified equations. You just needed to remember this. It can be R1 by R2 or it can be D1 by D2. Okay. If it is between two concentric spheres, A1 is 4 pi R1 square, A2 is 4 pi R2 square. So A1 by A2 ratio is radius ratio square, and F12 again here also is equal to 1. When you substitute that, you get this equation. Maybe my appeal to all my friends, whatever I am showing these equations, you need to remember them. Because there will be problems on this also. There will be problems on this. Please don't forget. This is very important. Or if you know all these conditions, just remember this equation. You can substitute all those conditions, but time consuming, right? It takes some time, to substitute the condition and derive that equation. But if you work a few problems, automatically these equations will be remembered by you. So now using radiation network, you can solve complicated systems of heat exchange between 3 surfaces, 4 surfaces, any kind of surfaces can be done. EB1, EB2, EB3, J1, J2, J3. Real surfaces, what leaves the surfaces, J1, J2, J3. Black bodies, what leaves the surfaces, EB1, EB2, EB3. Why we had to bring into picture here? Because EB1, EB2, EB3 are easy to calculate if you know the temperature of the surface. Black body temperature emission is sigma T power 4, simple equation. So because I know that, I need not worry about J1, J2, J3 because I have the surface resistance. And straight away I solve any complicated problem. Okay. So now towards the end of it, I just talk about radiation shields. 2 infinitely large parallel plates. What is the radiation heat exchange between them? It is A sigma T1 power 4 minus T2 power 4. You don't remember this? Here it is. Here it is. Here it is. Okay, 2 infinitely large parallel plates. So A sigma T1 power 4 minus T2 power 4 by 1 minus 1 by epsilon 1 plus 1 by epsilon 2 minus 1. That is the equation we have. Now, what happens if I introduce between the 2 surfaces, this is surface 1 and surface 2, I introduce a third surface, what will happen to the entire radiation? Now, let me not take too much of time on this. A third surface is always introduced and it is called a shield. Whenever a third surface is introduced between the 2 surfaces, the radiation heat transfer becomes reduced. And particularly, I was talking about liquid nitrogen, cryogenic temperatures, where insulation is very, very important for you. And in such cases, to reduce the radiation heat transfer, you introduce a shield. What if you introduce a shield? You get, 2 surface resistances into the picture now. Okay. If surface 3 is maintained at a third temperature, then it is EB3 and 1 minus epsilon 3 divided by epsilon 3 1 A1 and 1 minus epsilon 3 2 this side divided by epsilon 3 A2. So new 2 surface resistances come into picture, one facing this surface, another one facing this surface. Now, earlier, this 1 is exchanging heat with 2 and 2 is exchanging heat with 1. Now that you have introduced a new surface, now 1 is exchanging with 3, 3 is exchanging back with 1, and on the other side of 3, 3 is exchanging with 2, 2 is exchanging with 3. So that's how it is. Okay, so now with one shield, you have one more resistance coming into picture because of this forms into, these are 2 large parallel plates, these are 2 large parallel plates. So these three resistances and these three resistances are now all acted in series, and therefore this becomes this. And only you can apply any number of shields. You get so many resistances getting added to that, and if radiation between one and two, between two plates one and two, if n number of shields are introduced, see, this is one shield introduced. If you use two shields, three shields, that's what I call it as n. If n number of shields are introduced, then what happens to heat transfer? What was happening between 1 and 2, it becomes 1 by n plus 1 into Q1 to 2. Q1 to 2 is without any shield. What is the net radiation heat exchange they were taking place? Meaning this is the amount of radiation heat exchange that was taking place. Now with the introduction of the shields, what will happen to the net heat transfer? It becomes 1 by n plus 1 into Q1 to 2, where n is the number of shields. If you introduce one shield, n becomes 1, 1 by 1 plus 1, that is 2, into 1 by 2 into Q1 to 2. That means if you introduce one shield, what was the radiation exchange happening between the two shields? It is now 50% of it. It is now 50% of it. So by introducing one shield, you can reduce the heat transfer by 50%. Assuming that epsilon 1 is equal to epsilon 2 is equal to epsilon 3. Same emissivity surfaces are there, assuming that. So if two shields are used, n is 2, it becomes 3. If two shields are used between the two surfaces, the heat transfer that was happening earlier without shields, it is reduced by 1/3. It is reduced to 1/3. Okay, so here I have completed the entire radiation heat exchange. So very quickly, I just maybe leave you in 10 minutes. Maybe I just call it that way. Okay. I'm sorry, I was searching for something. Okay, let me go through in the next 10 minutes. Let me go through a few questions, whatever that we can solve. And I'm going to share this. In a radiative heat transfer, a gray surface is one. I told you difference between a black surface, gray surface, and a real surface. Black body is one which is ideal. White body is one which is ideal. White is one which reflects all the radiation that's falling in. Black is one which absorbs all the radiation falling on it, which emits maximum possible radiation. It emits radiation in all the wavelengths. Perfect. That's black body. A real surface behaves differently, and the emissivity of a real surface is always less than 1. And what is the difference between gray surface and a real surface? I told you that for a gray surface, monochromatic emissivity is always constant. At all wavelengths, its emissivity will be constant. For a real surface, that will not be there. Okay. So that means what? If lambda, emissive power, okay, E B lambda, for a black body, E lambda, emissive power, let me say, let me not use E lambda, okay. For a black body, if this is it, for a gray body, it will be less than a black body, but almost following a similar trend. For a real surface, it varies. So that means if you calculate the emissivity, what is emissivity? The emissivity power. At this wavelength you calculate, real surface ki emissivity power is this. This is the emissivity power of a black body. At this wavelength, when you see this is the emissivity power of a real surface, This is a real surface, this is a gray surface, this is a black surface. Okay. So, the emissive power of the real surface is fluctuating at wavelength. In one wavelength it is higher, in another wavelength it is lower. Whereas a gray body, more or less, it is same. So the ratio between these two curves will always be constant, almost very approximately. I cannot say exactly, approximately constant, not really varying for a gray body. For a gray body. Okay, that is the difference between real surface, black body, and a gray surface. So, what is the gray surface which appears gray in our to eye? No. Whose emissivity is independent of wavelength, emissivity is constant, just the way I have explained. Which has reflectivity equal to 0? No. We never said for a real surface reflectivity is 0 or gray surface reflectivity is 0. Which appears equally bright from all directions? No. So, emissivity is independent of wavelength. That is the answer. Okay. Radiative heat transfer is indented between the two inner surfaces of two very large isothermal parallel metal plates. Two large parallel metal plates. While the upper plate is designated as plate 1, is a black surface and is warmer one at a pine two plates on a pine black surface. And it is warmer and a hotter rather, which is at 727 degrees centigrade. Degree centigrade, we never use it. Plus 273, immediately you add. Okay, that becomes 1000. Okay, the lower plate, plate 2, is a diffuse and gray surface, meaning it's a real surface, I mean, not a non-black body surface. And emissivity epsilon is 0.7 and it's kept at 227 degrees centigrade. 273, you add it 500 degrees. Assume that the two surfaces are significantly large to form a two-surface enclosure and steady state conditions exist. Stephen Boltzmann constant is given. So, he is talking about two parallel plates. He is talking about two parallel plates. This is a black one, which is maintaining at T1 1000 Kelvin. Okay, 1000 Kelvin. The second one is a real surface. It's T2 is 500. Okay, Kelvin, Kelvin, and emissivity is 0.7. Epsilon 2 is 0.7. These are the conditions given, and surfaces are infinitely large, very large, he said. Now, what is he asking about this? Okay, one question based on that. The irradiation for upper plate is the amount of the amount of radiation. Irradiation means how much of radiation is falling on surface 2, surface 1. Irradiation is how much of radiation falling on surface 1. So for this data, okay, what is the irradiation coming on it? So how much is the irradiation coming on it? Now, what is coming? It's a real surface kada. How much is coming on it? J is coming on it. Okay, J2. ఎందుకంటే there are two large plates, as a shape factor is equal to 1. F1 to 2 is 1 and F2 to 1 is equal to 1. That means they are infinitely large parallel plates. There is nothing to escape. So from this plate, how much is coming? J2 is coming. What is J2? You know that. EB2 and J2, in between that, it is 1 minus epsilon 2 divided by epsilon 2 A2. Okay. So, you know J2, you need to, EB2, epsilon 2 A2, and you have to calculate only J2. That the radiosity of second surface is irradiation to the first surface. And what is the net radiation heat exchange between them? Q1 to 2 is equal to A2 parallel plates. A sigma T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This is the standard equation. And epsilon 1, first surface is a black one. This is 1. 1 and 1 cancelled. So Q1 to 2 is equal to Q12 is equal to A epsilon 2 sigma T1 power 4 minus T2 power 4. అంతే కదా. So there are two parallel plates. Q12 you could calculate. Epsilon 2 ఇచ్చేసిన 0.7. A of course per unit area తీసుకోండి. So from this, what is it? No, this is equal to J1 minus J2 divided by 1 by A1 F1 to 2. A1 F1 to 2 is equal to 1. And therefore, this is EB1 coming out of it. And therefore, shape resistance is 0. J2 can be very easily calculated. J2 can be very easily calculated. So, that's you can just perform calculation in kilowatts per meter square. Maybe you get 2500 and kilowatts lo icharu kabatti 2.5. If a plate 1 is also a diffuse gray surface with an emissivity value of 0.8, the net radiation heat exchange between plate 1 and 2. If you don't just come here. Plate 1 is not a black plate, it has emissivity 1. Okay. So, okay. So, what is this equation? Q12 net radiation heat exchange is A sigma T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So, epsilon 1, epsilon 2 values you substitute. Yeah, of course, per unit area you calculate. Q1 to 2 by area is equal to sigma T1 power 4 minus 1000 power 4 minus 500 power 4 divided by 1 by epsilon is 0.8 అన్నాడు కదా plus 1 by 0.7 minus 1. So that's how you calculate this. The following figure was generated from experimental data relating to spectral black body emissive power to a wavelength at 3 temperatures T1, T2, T3. The conclusion is that the measurements are okay. Ila ichadu. He has conducted an experiment at 3 different temperatures. He has drawn the experimental curves like this. దీన్ని బట్టి మన ఇన్ఫరెన్సెస్ ఏంటి అంటున్నాడు. Correct, the experiment is found to be correct because maximum EB lambda show the correct trend. Correct because Planck's law is satisfied. Wrong because Stefan-Boltzmann's law is not satisfied. Wrong because Wien's displacement law is not satisfied. నేను చెప్పాను కదా Wien's displacement law ఏమవుతుంది మీకు ఏం చెప్తుంది Wien's displacement law? The temperatures పెరిగేసరికి the peak temperatures move towards left అంటే పీక్ ఇలా ముందుకు ఇలా పక్కకు జరుగుతూ రావాలి. హైయర్ టెంపరేచర్స్ లో ద పీక్ ఈబీ లాంబ్డా ఎక్కడ వస్తుందో అది తక్కువ వేవ్ లెంత్ వైపుకి వెళ్తూ ఉంటుంది అని చెప్పండి. కాకపోతే ఇది డిఫరెంట్ ఉంది. లో టెంపరేచర్ కి తక్కువ వేవ్ లెంత్ లో వచ్చింది. as the temperature is increasing, wavelength at which the maximum emissive power is occurring is increasing. So therefore, wavelength cannot increase. It's a violation of Wien's displacement. Straight away. So D is the answer. A halo enclosure is formed between two infinitely long concentric cylinders of radii 1 meter and 2 meters. Radiative heat exchange takes place between the inner surface of the larger cylinder surface 2 and outer surface of smaller cylinder 1. The radiation at a smaller cylinder is labeled 1, outer cylinder is labeled 2. Radii is R1 is equal to 1 meter, R2 is equal to 2 meters. The radiating surfaces are diffuse and medium in the enclosure is non-participating. The fraction of thermal radiation leaving the larger surface and striking itself is. ఏమడుగుతున్నాడు వాడు చెప్పండి, ఏమడుగుతున్నాడు చెప్పండి. He is asking F2 to 2. Two long cylinders, concentric cylinders. ఇది 2 అంటాడు, ఇది 1 అంటాడు. లీవింగ్ సర్ఫేస్ టు స్ట్రైకింగ్ ఇట్ సెల్ఫ్ ఈజ్ అంటే అదేంది F2 to 2 ఎంత అని అడుగుతుంది. మీకు స్మాలర్ సిలిండర్ అనే లార్జ్ ఎన్క్లోజర్ F1 to 2 is equal to 1 కదా. And going by reciprocity theorem, A1 F1 to 2 is equal to A2 F2 to 1 కదా. ఓకే, సో A1 A2 దీని రేడియస్ ఇచ్చేసాడు కదా, మీటర్ లెంత్ అనుకోండి. సో వాట్ ఈస్ సర్ఫేస్ ఏరియా, pi dl or 2 pi rl, whatever you call it. Okay, so A1 is pi d1l, 1 meter ఇచ్చే d1, A2 is pi d2l, l is 1 meter అనుకోండి, d2 is 2 meters అన్నాడు. సో A1 A2 is calculated, F1 to 2 is 1, ఎందుకంటే దీని మీద నుంచి వచ్చే రేడియేషన్ కూడా it will be intercepted. Okay, so similarly F2 to 1 calculate చేయొచ్చు మీరు ఇప్పుడు. You know A1, you know F1 to 2, you know A2, F2 to 1 can be calculated. Now 2 అనే సర్ఫేస్ దేంతో ఇంటరాక్ట్ అవుతుంది రేడియేషన్ ఎక్స్చేంజ్? 2 is interacting with 1 and 2 is interacting with 2 itself. అంటే some of the radiation leaving 2 is falling on 2 itself. So it is effectively summative rule తీసుకుంటే F2 to 1 plus F2 to 2 should be equal to 1. That is the summative rule because it is interacting with only 2 surfaces. 2 is interacting with 1, 2 is interacting with 2 itself. So F2 to 1 plus F2 to 2 is equal to 1. F2 to 1 ఇక్కడ calculate చేసావు నువ్వు. F2 to 1, F2 to 2 you can calculate. So from this. So whatever. Right? So you get 0.5. Circular tube of equal length and diameter shown below. The view factor F1 to 3 is 0.7. The view factor F1 to 2 in this case will be the plate, the base is A1, another base is A3, the surface is A2. So what is he asking? What is he asking? For a circular tube of equal length and diameter shown below, the view factor F1 to 3 is 1 to 3 is 0.17. The view factor 1 to 2 in this case will be. Okay, so in what is 1? 1 is a base. What is it? Flat surface. 1 is interacting with 3, the curved, the other surface, and the curved surface 2. 1 cannot interact with 1 itself. So F1 to 2 plus F1 to 3 is equal to 1. F1 to 3 is 0.87. F1 to 2 is 0.83. Quite obvious. అంతే కదా. F1 to 1 is a flat surface. దాని నుంచి వెళ్ళిన దాని మీద పడే ఛాన్స్ లేదు కాబట్టి it is now interacting with only two other surfaces, 2 and 3. So F1 to 2 is 1 to 3 is 0.17 అయినప్పుడు F1 to 2 is 0.8. What is the value of view factor for 2 inclined parallel plates? This is an equation. You just can go through it. So many such problems you can calculate. Okay. So straight away there are problems on using this. I just asked you to remember 2 infinitely large parallel plates. Okay, I'll update all this. Maybe you can go through it, my dear friends. Maybe I'm coming to an end here. If no, my appeal to you is, see, if all those who heard me, you please raise your queries whatever you can. I'll give you a week time from here on, and you within a week time you just go through the entire presentations what I gave, and any doubts that you're getting, you can mail it to me. Continue to mail it, or you can, the way you were giving a feedback, you continue to give. I'll request the authorities of JNTU to send back those feedback or queries to me, and I'll take another week time and send it back to each one of you. Okay, or I'll make a presentation of that kind and keep it in the website. I just should thank you for giving all your patient listening, and I don't know how far it was useful, but the very intention of me participating, in spite of all my activities, is that I just wanted to inform you that everyone in the state of Andhra Pradesh is very serious about regaining the past glory. That's what I was telling about the Vrindavan at Madura. So we are very serious about regaining the past glory, particularly in terms of cracking the competitive examinations by Andhra students. So the mission is now every senior professor in Andhra Pradesh is committed to bring back this seriousness into the classroom of every university or college within Andhra Pradesh. Now, I make an appeal through this platform to all of you, my dear friends. Just don't take things very easy. Now, I know there are many distractions for you. Electronic gadgets have come, social networking is there, and a lot of movies, a lot of fun clips, and a lot of time can be spent without realizing on your smartphones and laptops. I know, but at the same time, there is a purpose. At least as long as you are a student, you cannot be completely onto a relaxation mode. Relaxation should be there only for whenever you get bored or whenever you wanted some relief in between. But your major role, primary role is to you know achieve something as a student and make every one of us, your parents, your society, everyone so proud about your achievements. The effort made by us, it's not that your teachers are not teaching it transfer. Just because when people like us we participate in this, at least you will understand the seriousness the state government and the universities and the entire teaching community is. Particularly in COVID, we need to be different from tomorrow onwards. So please, my dear friends, take this message. I cannot give you a longer message than this. Thank you very much for a patient hearing, and all the very best to you. As I've told you, next 1 week, you compile all your doubts in heat transfer, send it to me. Thank you. Bye bye.